Hello and welcome back to the Apprentice 1-to-1 podcast. It is me, Mark, and we're back again with episode 3 on the design series. Craig's back with us. First up, how are you this evening, Craig?
Yeah, good, thank you. Usual busy life and balance, but all good tonight, thanks.
Good stuff. And this one is your baby. You've come up with the concept here and been ably assisted by Richard in putting it together in a presentation to follow along from the lines of last week. How are you doing, Richard?
Very well, mate. Thank you. Very well. Battling on as you do in our wonderful world of electrical installation. But yeah, all good, mate. Looking forward to it as always. Yeah, happy days. You all right, mate?
I'm not too bad, cheers. Same old. Too busy on roofs, getting sick of solar already, but there you go. It is what it is. I signed up for it, so I'm seeing it through. But This week, again, we're going to delve into the world of design, and we're kind of taking it on this journey as getting more complicated, I guess is the right way to put it each week. Started off with a simple lighting circuit. Myself and Richard ran through a slightly more complex shower circuit last week, and Craig's come up with this one. So I'm going to zoom us all down off the screen again. Hopefully this works, and bring the slides into play. And we'll start with, as we did last week, the scenario itself. So hopefully you two can see that. Is that coming up on the screen?
Yeah, that's pretty good. Pretty good.
Yeah,
it's pretty good.
Good. So are you going to lead the discussion through this, Richard, or is Craig doing it? Are we going to take it forward on this chat through?
Yeah, I think so. I think I'll go through it, and then obviously it's Craig's little baby. But I think I've captured most of the information. But Craig can chip in and bits and pieces. We just bounce off each other as we did last week, if you like.
Yeah,
we don't have a Mrs. Smith this week. It's Mr. Jones, and he owns a small little factory unit, and he's just purchased himself a brand new compressor. So, got a bit of information regarding this compressor. It's a 3-phase, 400-volt compressor, 15 kilowatt. So it's quite a big boy. It's got a power factor, I should have said, 0.8. I'm sure Craig will refresh our memory on what that is in a bit. Bit of other information regarding noise levels and air pressure, etc. So quite a bit of information electrically that we're going to need. Our existing consumer unit this time, because it's a 3-phase installation, it's an 8-way TPNM board, and it's got 125 amp main switch incomer. Cable we're going to be using this week is a 4-core multi-core armoured 70-degree thermoplastic insulated conductors, copper obviously. The circuit's going to be installed at a depth of 1.75 meters inside a ducting, obviously under the ground. Got a circuit length of 43 meters, a bit less than last week. And with this one, we're going to run a separate CPC with that 4-core multi-core armoured cable, but it's going to be 2 cross-sectional area sizes smaller than the live conductor cross-sectional area that we're going to select in a bit. We've got a highest ground temperature expected of 35 degrees C, and our supply characteristics are a TNS system with a ZE of 0.24 ohms. So I think I've captured most of it. A bit on power factor. What's that all about, Craig?
So power factor is basically a correction to bring us closer to unity. So it's your measure between your true power and your apparent power, which you would have covered in your science and principles for your installation. But we need to effectively balance the loads as best as we can throughout the installation and make sure that it's running the way it should be. And therefore, when you have 3 phases, they're not all running succinctly in the perfect pattern with each other. So you can use power factor to bring that much closer to how you want the system to be operating. I think that's kind of where I was planning to go with that tonight, rather than delving way back into science and principles, but just looking at the relationship of voltage won't always be set the way it is, current won't always behave, so power factor will allow you to adjust that in a manner to account for differences and tolerances within your circuit, really.
Okay, so, and we need to include that within our calculations, because what effect does it have generally, the power factor?
Well, power factor will generally increase the size of the current that's taking place in the installation. So you have to allow for it because your equipment demand is going to be of a higher level when you're looking at your protective devices and your cable selections further down through the calculation in that install.
So hopefully we're going to see it factored into our equation in a minute.
Yeah. Fingers crossed if I can make the slides work properly. So in essence, it's making sure we don't undersize our our cabling, isn't it? I think, and there's a lot more information on this. I can see straight away for those people who've watched the last couple of episodes. We've got loads more information in there, which is obviously going to be needed in some of these calculations. Shall we move across to the next slide and see what info we've got? Oh, wrong way. So this is the key
scenario,
information.
and like we were talking about last week, I always find it easy to, out of the scenario or the question, is to pull out the more important bits of key information, and then you can consider those in your design. So again, quite simple really, but got a little image of the building type, little small commercial unit, picture of our earthing system, picture of the three-phase MEM Eaton board, loads of those about, cable type, picture of what that's going to look like, your single insulated CPC that we've got to install separately, circuit length, as we've said, 43 metres, highest ground temperature, we're expecting 35 degrees C. And our cable installation, we know that it's going to be inside a duct in the ground at a depth of around 1.75 metres. So all that information is important. If I can gain further information from that, i.e. installation method or reference method, etc., that's going to help me when I lay out my calculation, because all I've got to really do is follow the steps and input the information into the various formulas to find the correct information from tables, etc., etc. So I always do that because it kind of simplifies things out, just makes it a bit easy. And sometimes a picture kind of brings to life the scenario, if that kind of makes sense. So, hopefully that makes sense.
There's been some positive feedback on the visualization that you've done of this, Richard, from last week. A few people who have issues with dyslexia and taking in information and content out of the textbooks and even at college, and they found that really useful. Although this is a podcast, it's obviously audio, looking at it visually really did bring it to life for them. So, credit to you for going to the time and effort of putting that into place.
That's all right. I mean, back in the day when I used to deliver it, I used to produce stuff like this, but then I'd also have a bit of SWA to hand around, and, a thermometer I'd leave on the table, and get a three-phase board of the same manufacturer if I could. Little sample of a earthing arrangement, a photograph of a real life one. It just kind of brings it to life a bit more. If you can pick someone up and look at it, you can familiarise yourself with it, because not everyone might have seen SWA or an old MEM, three-phase board or whatever. Do you know what I mean? Kind of makes
Definitely.
I mean, I was going to go and dig my garden up and put some ducting in at 1.75 metres, but I've been a bit busy today. But, it just kind of adds a little bit of value to it. And for some people, it helps them visualise what it is exactly we're talking about. And it helps them with the design a little bit, So trying to simplify and make it easier.
And as we said last week, I'll add this onto the website again. There'll be a link in the description to go and download the PDF. For anyone who wants to refer back to this later, it will all be there. So, have I gone the wrong way again?
Yeah, you're right.
Actually, I don't think I have. That's
then you've got to go the other way.
Oh, geez. What is going on? There we go.
That's the one. That's it. So all I've done again is laid it out in exactly the same way we did last week, in exactly the same stages we're going to follow through. There's a little bit more to think about in this one because Craig's chucked a few curveballs in, but it's kind of the same process. We might have to look in other tables or different tables than we did last week. Some of the tables we're going to be using today, they're not in the on-site guide, because obviously the on-site guide is a simple guide to simple stuff, really. So we're going to be looking in the regs a little bit more today, but I've had a little bit more time today, so I've managed to snippet out some of the tables that we're going to be discussing and drop those into the document. But if you're following and not watching, obviously you can flick through the regs, but we've got page numbers, etc., to find the right tables and page numbers. So same as we did last week, first thing we need to consider then is we've got to determine our design current, and remember that the symbol for that is IB. We've got to consider as well, as we said earlier, that we've got a power factor of 0.8 to consider. So the formula to calculate design current on a three-phase system, similar to last week, but of course it's three-phase. So we've got to divide our power, which in this case is 15 kilowatts, so 15,000 watts. Got to divide that by the square root of 3. Got to times that by our line voltage, which is 400 volts, and times that by our power factor of 0.8. So as Craig said, if we don't include the power factor of 0.8 within that calculation, we're going to calculate the design current incorrectly, Because we've got 0.8 power factor in, we do that calculation and we get a design current of 27.063 amps, and we generally round that up to 27.1 amps. So 27.1 amps is our design current, and that'll be per phase, won't it, Craig?
Yeah, and that's the point of the three-phase sort of element of the calculation, is it's giving you a current per phase to work from, and that then gives you your breaker size and your cable sizes, because people often don't understand that, as you say, it is per phase rather than an overall sort of current. So to calculate that effectively.
If it was a single phase compressor of the same power rating, same power factor, what would that do to the current? If it was single phase and we still wanted a 15 kilowatt compressor,
it'd bump it up considerably.
Yeah, it would give you a much bigger cable and a much bigger breaker size, wouldn't it? So by putting it across three phases, you can start to reduce that down.
Yeah, so more efficient in it, better way of doing it.
Yeah,
better way of doing it. Happy days. So 27 amps is our design current. Last week, and prior to that, Craig had a good conversation about diversity and if we can apply that as a designer, etc. So I thought I'd ask the question again with this. We know that in the on-site guide, table A2, page 137 there, it gives us some guidance on applying different amounts or allowances of diversity depending upon the type of equipment and the type of premises. So again, I've just reproduced a couple of the bits out of that table there. We know that it's a commercial stroke business premises, so I've got to look in that column for business premises. It comes under small shop, stores and offices. Within the compressor, of course, is a motor, and other than a lift motor, we can't apply diversity because it's saying for a business premises, we've got to take 100% of the full load current of the largest motor. Because it's the only one in there, we'll assume we can't apply diversity. So design current is 27.1 amps. Happy with that?
Yep, I'm more than happy with that. Makes perfect sense to me.
Okay. So we got our design current IB. Then we can consider determining the rating and the type of overcurrent device, and do we need to consider additional protection if required? Well, the cable's going to be running, it's still wire armour cable, it's going to be running inducting, so there is no requirement for additional protection. So I've only got to think about overcurrent protection. I've got to think about then regulation 433.1.1, which considers overload protection. We looked at this last week. We've got to make sure that our rating of our protected device is equal to or greater than our design current, because if it's the other way around, you're going to get nuisance tripping from your overcurrent device, etc. So I've got a design current there of 27.1 amps. So I've got to select now a circuit breaker with a current rating equal to or higher than 27.1 amps. So we're going to select a 32 amp device because that's the next size up. But then I've got to think about either it being a type B, a type C, or a type D device. And again, last week we had a look in the on-site guide, table 7.2.7, indent 2 on page 90. Remember, that gives us applications for circuit breakers and what we can use type B, C, and D for. Now, because it's a motor and it's quite a big motor, there may be a possible inrush current to consider. So when we switch the motor on or the compressor, the initial inrush current may be quite high. And on a standard type B device, we only need between 3 and 5 times the rating of it, and it will trip out because it will think it's overloaded. Whereas a C type, we can go between 5 and 10 times. So it makes sense to pick a type C, 32 amp, 3-pole, 3-phase device. Then onto the MEM website, Eaton, MemShield 3, and yet they make one, still make one today, and it's fully compatible because it's their brand. So we're happy with that. So we're going to pick then a 32 amp type C device, 60898 circuit breaker, and is 32 amps equal to or greater than 27.1, which is our design current? Yes, it is. So we're happy with that. We've got our design current and we've selected our protected device, 32 amp type C, 60899. Happy with that?
Yep, that's all good.
Stage is done. Loving that. So next thing we've got to do is to determine our installational reference method. In other words, how is this cable being installed? So we know that it's a multi-core armor cable and it's going to be ran in a cable ducting direct in the ground. So I can look in table 4A2 in appendix 4 of the regs on page 437. It gives us numerous different installation methods. And when we look in table 4A2, reproduced it up there for us. We've got a nice little pictorial diagram. And it comes under number 70 within that table, and it's a multi-core armoured cable, either in a conduit or it's in a cable ducting in the ground. And it gives us a reference method there of D. Happy with that?
Can I just
happy with
that, but can I just point something out on there that is often missed, I think, by people, is that when it talks about installation method or reference method, the installation method is actually the numerical values going down the table. So you might have the same reference method of being bunched in conduit, for example, but the installation method is what then divides it up as to the type of situation that the conduit is then bunched in. So people understanding the difference of the reference method is B, C, D, E, wherever you're going, but actually having an installation method as well. So although the tables factor your cable calc usually on the reference method, it is important to go back and understand the installation methods are there at the same time and the difference between the two of them.
Yep. So your installation method is your number. And then obviously, as Craig said, your reference method will be a letter. As he's quite rightly says, you can have cables in ducting or with just buried in the ground without ducting. They'll still be D, but they'll be a different number. And that's important when we're looking to get the right information from our current carrying capacity tables that we're going to look at in a bit. So for this
electrical
example,
OM lays that out really well as well. I've got to say, before we move on, that they set that out really nicely from using that software.
Reference method D. Happy days. So we've got to consider now then what derating factors are there to consider within our little scenario. So we know that we've got an ambient ground temperature of 35 degrees. That's the maximum we're expecting it to go. So we've got to find the right table again within Appendix 4 of the regs. So within Appendix 4, we can look at Table 4B2 on page 441, and that gives us rating factors for ambient ground temperature, not to be confused with Table 4B1, which we used last week, that was talking about the ambient air temperature. We haven't got a factor for that one. We've only got a factor for the ground temperature because obviously the cable's going inside a duct in the ground. So we look down on the left, ground temperature, go down as far as we go as 35 degrees. We come across, and we already know that the insulation on our multi-core armoured is 70 degrees. So the factor there is 0.84. Nice and simple. Happy with that?
Yep. Excellent.
Yep.
And then we've also got to consider that the cable is buried. There's a little mistake there, direct in a duct. It says grouping, but it's not grouping, it's buried. That's me leaving it over from last week. So it's actually buried in a duct, and we've got to consider that this is going to have a derating factor as well, because don't forget, ultimately derating factors are allowing for the fact that the cable can't dissipate the heat, which will directly affect the current carrying capacity of it. So this one, we've got to look down in Table 4B4, and on the left, it's depth of laying in meters. So we know from the scenario that it's 1.75 meters down. Is it buried direct? No. Or is it in a buried duct? Well, we know it's in a duct. So the factor there is 0.94. Happy with that? So it's
a marginal difference, isn't it?
Yeah,
such
you
a
get the
tiny
right
amount.
And you get the right value. So 1.75 meters down the left, and then you've got to select the right table. Is it buried direct or in buried ducts? Happy with that? Okay, so now, based on those factors, we can then use our formula again to calculate the amount of current that this cable is going to need to carry, IZ. So we know that in Appendix F, the formulas are in there for us to use in the on-site guide, but also in Appendix 4 on page 425, it refreshes our memory on different formulas we can use and the different symbols. So to calculate the amount of current the cable is going to need to carry, one method of doing it is to divide the rating of our protector device and divide that by our two factors, our derating factors that we've just found. So it would be 32 amps divided by 0.84 times 0.94. So it will give us a total of 41 amps. So because the cable is in a duct and because of the high ambient ground temperature, that cable is going to need to carry 41 amps. Happy with that?
So now a bit of a difference.
Yeah. So I've got to select a cable now that can carry the 41 amps. So once again, I've got to get the right table. You won't find this particular table in the on-site guide. You've got to go into the regs books. It's got far more different types of cables, different tables. So again, within Appendix 1 in
Sorry,
the regs,
Richard.
go on, mate.
I was going to say one hint I would say to apprentices or people looking at doing the regs exam is marking up page 420 with page numbers as to where these tables are in the regs book. Makes it a lot quicker to navigate your way around to these specific tables to help you out when you're under pressure.
Contents page for every part of the regs is the place to go because it lists all the chapters and the sections and everything. Yeah, absolutely. So table 4D4A is for 70-degree multi-core armoured cable. I've got to get the right table for the cable I'm using. Okay. So within that table, I'm looking for the right column based upon the installation method of the cable. So I think I've included the table within the document here. So when you look in column 7 of that table, we go all the way down on the left to our different size conductors until we come to at least 41 amps. So I have a look down there, and 10 mil squared will carry, there it is, will carry 50 amps. Happy with that? So as we go down, 10 mil will carry 50 amps, whereas 6 mil will only carry 38. Is that right?
Yeah, that's right. Yep. And I think it's important that people make sure they are reading the single phase and the 3-phase column, because if you look at single phase, and a 6 mil would carry enough technically for the circuit.
Yeah,
I believe.
So you got to use the right column number, which is column 7, because it's a 3 or 4 core cable, and we're installing a 4-core 3-phase cable. Correct? So 10 mil,
yes,
50 amps. Can't use 6 mil because it'll only take 38. And we're looking for something that can carry at least 41. Happy with that?
Yes.
So for our steel armour cable, then we're going to be using, or we're going to select in 10 mil squared. Happy with that? Okay, good. So last week we had a bit of a moment where we've got to consider as well, Appendix 4 again, that statement that talks about you can calculate IT, but you can obtain it from a different formula, providing the circuits of that group, if they are grouped, are not liable to simultaneous overload. So circuits installed on its own. So I can use this formula instead to calculate the amount of current the cable is going to carry, but the only thing that changes is I'm not dividing the correction factors by the rating of the device because it can't overload. I'm dividing it by the design current, and the design current is 27.1 amps. You can never overload this thing. So what does that do? Well, actually, it alters the amount of current that the cable is going to have to carry. So instead of it having to carry 41 amps, it's only got to carry 34 amps. So do I still need 10 mil? No. I can put in 6 mil. And there's a picture of some guy with a load of cash in his hand. Is it going to save us a bit of money, 43 meters of 10 mil compared to 6 mil?
Just a bit.
So again, just a little bit of something to think about as we did last week. I can consider this other formula, this other way of doing it, because it is in the regs. It's an alternative way, as long as the circuits that are grouped, if they're together, or the circuit itself is not liable to overload, and it can't overload, can it? So therefore, 34 amps is all the cable needs to carry. 6 mil will do it. Happy with that? But again, something to think about. And of course, it complies with 433.1.1 because the rating of the cable needs to be equal to or greater than the rating of the device. So we're happy with that. Okay, we're going to base it on 10 mil. So we're going to go the way that we went originally. So everything else is based on that 10 mil cable. So we're still going with 10 mil. So then we need to consider the actual volt drop on that cable that we've selected based on the length and the design current and everything else. So again, last week we looked at this formula that we can find in the on-site guide in Appendix F on page 168. It's also in the regs book, but it's in words as opposed to in a formula. So to calculate volt drop then, we need to know the millivolts per amp per meter value for the cable we selected, 10 mil. We need to times that or multiply that by our design current. We know what that is. Times that by our length. And we've got to divide it by 1,000 because we want the answer to be in volts and not millivolts. So the first thing to do is find the right table again in the regs book. And in the regs book, the volt drop tables generally follow the current carrying capacity table. So the current carrying capacity table was 4D4A. So therefore, the volt drop table directly underneath it is 4D4B. So I've got to go down on the left to my selected cross-section area, which was 10 mil. Got to go across then, and I know what Craig's going to say. You've got to be careful here which column you use. So column 2 is for 2-core cable DC. Well, we're not DC, we're AC. It's not a 2-core cable, so we can't use column 3. It's not single phase. I've got to use column 4, which is a 3 or 4-core cable, 3-phase. So 10 mil squared, come all the way across, and my millivolts per amp per meter value is 3.8. So for every meter of that 10 mil cable, it's going to lose 3.8 millivolts per amp per meter. All I've got to do then is put those values into my formula to calculate the actual volt drop. So 3.8 millivolts per amp per meter, multiply that by my design current, which was 27.1 amps, multiply that by my length, which was 43 meters, divided by 1,000, so I've got the answer in volts, and I get a calculated volt drop of 4.43 volts. Okay, so is that acceptable? Well, again, last week we looked at table 4AB in the regs book on page 430, and I've replicated it and put it in this document for us to refresh our memory on it. And we know for circuits other than lighting, we're allowed 5% of nominal, and nominal voltage is stated as 230 volts. That's our voltage to earth. So therefore, the maximum volt drop we're allowed on anything other than lighting is 11.5 volts. I can't go above it. We've just calculated our volt drop at 4.43, and therefore it's equal to or less than 11.5 volts. So our calculated volt drop is less than the maximum allowed. So that 10 mil cable is all good for volt drop as well. So it's good for current carrying capacity, and it's good for volt drop based on 43 meters. Got a copy there of 6.4 out the regs book with table 4AB, and within it, it says the volt drop between the origin of an installation and any load point should not be greater than the values in the table below, expressed with respect to the value of the nominal voltage of the installation. It does, though, say in one of the little notes that you may have a greater volt drop when motors are starting, etc., and that is acceptable. So we might have an initial volt drop once our compressor starts up. You'd expect that. That's not a problem. Happy days. So far, we've done our 3 or 4 stages, and we've got as far now as confirming volt drop, and all that's good. So 10 mil in terms of current carrying capacity is good. We're happy with that. Next thing then we've got to consider is to determine our maximum disconnection time for this circuit. So in other words, what's the maximum time before our protected device needs to disconnect based on our chosen protective measure? So we're going to be choosing automatic disconnection of supply, as we did last week from chapter 41. So again, we can find that information in chapter 41, pages 64 and 65. And we're going to specifically be looking now at regulation 411.3.2.3. This gives us information to determine the maximum disconnection time based upon the load and based upon the earthing arrangement. So maximum disconnection times that are stated in table 41.1, I've included the table in here, shall be applied to final circuits with a rated current not exceeding, so 63 amps, 1 or more sockets. This circuit isn't a socket outlets, or up to 32 amps applying fixed connected current using equipment. Well, this circuit is 27 amps and it is a piece of fixed current using equipment. So what we need to do now is look in table 41.1, and we need to have a look at the earthing arrangement to find out what our maximum disconnection time is for this circuit. So table 41.1, our nominal voltage is between 120 and 230. So I'm using the second column in. It's on a TN system, it's AC. So therefore our maximum disconnection time is 0.4 seconds. So this type C 32 amp breaker has got to disconnect in the maximum time of 0.4 of a second. So just under half a second, we've got to make sure that's what happens. Okay, last week it was 5 seconds, but this week, super quick this week, 0.4 seconds. We've got to make sure that happens. So we need to confirm it. So the next thing we need to do is to determine the maximum earth voltage impedance value to achieve that 0.4 second maximum disconnection time. So again, I can go and have a look when we check for shock protection, the maximum ZS values. So before we get to that, we need to calculate what our ZS value is going to be, and we're going to compare it with the maximum allowed. So going back to the scenario, we know that we've got to run a separate CPC with this SWA, and we know it's got to be 2 sizes smaller than what we've selected for our line conductors, our live conductors. So 2 sizes smaller than 10 mil will be 4 mil. So we're going to run this 4-core 10 mil in, and we're going to run alongside it or with it a single insulated 4 mil CPC. So we need then to find out what our resistance value is in milliohms per meter for our combination of 10 mil line conductor and 4 mil CPC. So we won't find this in the regs. This information we need to get from the on-site guide, from table I1 in Appendix I. So we're going to look down in that table until we come to 10 mil for our line conductor and 4 mil in our CPC. When we look in that table, we should get a value then for 10 mil, 4 mil combination of 6.44 milliohms per meter. So for every meter of that combination, 10 mil, 4 mil, we're going to have 6.44 milliohms of resistance per meter. So my formula to calculate ZS, again, it's in the on-site guide, is ZE plus R1 plus R2. So we know what our ZE value is. We've got that from the scenario. What we need to do now is calculate our R1 and R2 based upon the length. So to calculate R1, R2, we need our milliohms per meter value that we've just got from table I1 of the on-site guide. We need to apply a multiplier, which we can find from table I3, and that's to allow for the fact that that conductor under fault conditions is going to rise. That value is 1.2, and we need to times that by our length, which was 43 meters. So if we do that calculation, we're going to get a total R1, R2 value of 0.3323 ohms, rounded down 0.33. So I add that to my ZE value of 0.24, and I get a total earth fault loop impedance value of ZS of 0.57 ohms. Happy days. So what do I do with that 0.57 ohms? Well, what I need to do now then is to confirm that that value of 0.57 ohms is less than the maximum value I'm allowed for that 32 amp type C device. So I'm going to go into table 41.3 of the regs, and I'm going to go until I find type C circuit breakers to 60898. So not the first row, the second row down, type C. I'm going to go across to 32, and I'm going to find what the maximum value of ZS is of 0.68 ohms. So is my 0.57 under 0.68, which is the maximum? Yes, it is. So therefore, in theory, that circuit breaker should disconnect within my maximum time of 0.4 of a second. Happy days. So far, it's worked out quite well. So far, so good. Happy with that?
Very much so. You're doing a sterling job, Richard.
Right. So to confirm that, we're also going to look then at calculating the fault current. And by fault current, I'm going to expand a little bit more than we did last week. When we're calculating fault current from this point, we're using our UO value, our voltage to earth. So this is our prospective earth fault current value that we're calculating. So again, we can find it in Appendix F, or I and F, sorry, of the on-site guide, and it gives us a formula. So to calculate our fault current, IF, we need to divide our nominal voltage, 230 volts, by our value of ZS to get a fault current value. And again, it's just Ohm's law. So our fault current, based on our 0.57 earth fault loop impedance, is 403.508 amps. In other words, about 404 amps of current that would flow if you had an earth fault. So another thing to consider, and we won't do it this week, but do we need to consider our prospective short circuit current, PSCC? Do we need to consider this? So this, we check in to make sure there's enough current there to disconnect our device within a certain time under earth fault conditions. Do we need to consider it under short circuit fault conditions? I mean, we're all used to doing, earth fault loop impedance tests and values and all the rest of it, but do we ever do a line neutral or a short circuit test to ensure the device is going to disconnect? I certainly know that 2396 expand upon calculating short circuit, don't they, Craig?
Yeah, they do. And I think it's often a test that people miss in the field as well. When you're doing your ZE at origin, you are supposed to be breaking down your prospective fault current and the two components that go with it and measuring the difference between the two. And you'll generally find your short circuit current is the one that you need to record under your PFC. However, as we say, it's often the skipped test and definitely the skipped calculation, I would suggest. But yeah, I think on our next scenario in the following weeks, we definitely need to start expanding on that and opening up eyes, because between line and neutral could be more damaging. Right?
Yep. So, we're considering shock protection. We're considering under earth fault conditions, is this device going to disconnect quickly enough? But do we need to consider if there's a short circuit, or indeed I grab hold of the line of neutral? I want that device to disconnect as quickly as I can, because the longer I'm attached to it, the more current there is, the more damage it's going to do. So a thought for you to think about. Again, send any theories you have, or do you think we need to or not, or, send those in. Something to think about. We'll expand upon that. But so far, we've worked out our prospective earth fault current. We've got a value of fault current. So what I'm going to do now is confirm the actual disconnection time of the device that we've selected is going to be within the maximum that we're allowed. It should do, because we've checked it with our max ZS, but we're going to actually go and make sure it can. So again, we had a bit of a look in Appendix 3 last week in the regs book, and within here, it's got all our time current information for all our different devices. So based on current, we can find out the time it will take for a device to disconnect, or based on time, we can calculate how much current we're going to need, etc. So I've got to choose the right table, the right figure, as they are in Appendix 3, for the devices that we're using. So figure 3A5 is for type C circuit breakers to 60898. That's what we've got. So we've got our time current graphs on here. To simplify it out, they've produced this nice little table on the right for us. And we can see here how much current we're going to need for each of these devices to disconnect that device between 0.1 of a second, instant, to 5 seconds. I need my device to disconnect in 0.4. If I've got enough current in this table, it's going to disconnect it instantly. So I can look down 32 amps. I need a current of at least 320 amps. And I know that we've just calculated that we've just got 400 and some amps, wasn't it?
404, I think, yeah.
404 amps. So that's more than 320. So based on that impedance and that voltage, that device is going to disconnect instantly. So I've smashed my 0.4 second disconnection time. It's actually going to disconnect instantly. So all good with that. Right, then, the last thing we've got to check is our 4 mil CPC that we've selected, that we're going to run alongside this SWA. We've got to make sure that the cross-sectional area of that cable, 4 mil, is acceptable based on that amount of fault current, based on that duration of time before the device disconnects, and based on the coefficient of the material that's used, in this case, copper. So last week, we had a bit of a look at Regulation 543.1.3, which talks about the minimum size CSA of the CPC that's required. And it gave us the old adiabatic equation. So to calculate it, we need to square root the amount of current that we've just previously calculated squared, times by the time. We know that because we just calculated that. And we need to divide it by our K value. So we know that in the various tables in Part 5, Chapter 54 of the regs, it gives us K values depending upon how the protective conductor has been ran, if that makes sense. So what we've got to do is select the K value for the cable, the 4 mil cable that's been ran with the SWA. And I've already spotted a mistake that I've made because I've selected the wrong table, which is good. So in table 50, part 5, in chapter 54, we're looking for the right table where the protective conductor is not incorporated in the cable, or it's not bunched. So it should be table 54.2, I think. So let me just have a little flick through here, because being lazy, I've just used the same table that we used last week. So
an easy mistake to make.
Yeah, so table 54.2 is for insulated protective conductors not incorporated in a cable and not bunched with cables.
So that's what we've got here. Yeah, so it's not incorporated in a cable like it was last week, because we had a flat twinning CPC cable. This is being run separately. So in that table 54.2, I'm going to look down for the material of the conductor. We know it's copper, okay? And the insulation material is 70-degree thermoplastic. So our K value is actually 143, correct?
Yes.
143. So our current, we know, we've just calculated that, was 404 amps, okay, squared, times our disconnection time we've got from Appendix 3 of 0.1 second. We're going to divide that by a K value of 143. So let's do that now. So square root of 404 squared times 0.1 divided by 143 equals. So I've got a minimum cross-sectional area that we're going to need of 0.89 millimeters squared. Based on that amount of fault current, that amount of time the device is going to take to disconnect, and the K value based on the protective conductor that's not running the same cable, it's not incorporated with it, it's run separately. So K value is 143. So the minimum size that we need to run with that SWA is 0.89 millimeters squared. We've actually selected a 4 millimeter squared cable so that can cope with that amount of current for that amount of duration before it disintegrates. So 4 mil is plenty big enough. You could have run a 1 mil with it if you can get it anymore. 1.5 would have done. 2.5 would have done, but 4 mil is all good. Happy with that?
Yeah, and I think just pointing out for people that there's a fine line, isn't there, between having a massive CPC conductor, but having one that's too small, the layoffs to each other. As the smaller the conductor, the less ZS you're going to have potentially in the circuit with a bigger conductor, but the bigger conductor has a bigger cost. So it's a real design balance borderline for people when they're doing this.
Yeah, it is. I mean, some people might be thinking, well, why didn't you just use the steel or armouring of the SWA? But that's a further calculation, which I'm sure we can look at. We can expand on that another week, can't we? Because you need a different table for your K values. So to summarise it, our chosen cross-section area of our steel wire armoured cable of 10 mil and our separate 4 mil CPC will fully comply, of course, with all the relevant parts of 7671. So I could go ahead and order that cable now, all those cables. I could install those, put those in, and it would be fully compliant with the regs. We're happy with that. Again, another question a bit similar to what we asked last week. Could we design this slightly differently? Possibly. Could we use the steel wire armourings of the SWA for the CPC instead of running a separate one? Maybe we can look at that another time. And interestingly, we spoke about using software last week. Me and Mark had a bit of a chat. And I've got a very simple megavolt drop and cable calculation app on my phone. So I pumped in 15 kilowatts, voltage of 400 volts, and a cable length of 43 meters. It doesn't ask for any other information than that reference method buried in the ground. It asks for that, etc. And it actually recommends a minimum cable size of 6 mil. Interesting. But if it's used the alternative method of calculating it from design current, like we mentioned earlier, then potentially that's what it's done. But interesting.
You would hope that it specified that, though, wouldn't you, as to what way you were doing it? But
yeah, it's not. It's very simple. I don't have
good guide though.
Yeah. I mean, it gives you a rough idea, but it actually states, as soon as you click onto the app, you must verify it, with all the requirements of the regs before. But it gives you an idea. And as we said earlier, 6 mil would have been fine as far as current, IT goes. You'd have to further then calculate it for volt drop and all the rest of it. But that's for the listeners to have a go at themselves, basically. But just another example of another very simple cable calculation based upon a certain scenario with certain factors thrown in. Nothing too overly complicated, but this time it was 3-phase, bit of power factor, slightly different correction factors, different installation method. But the process we followed last week, same process we followed this week, and ultimately you're just verifying at each stage that it's fully compliant with 7671, and if it is, happy days.
And I think it's hugely important. The reason I went for a duct and a ground is because I had a real life scenario in a similar situation. It wasn't for a motor, but actually using the regs and how you apply meant the difference between pulling in 300 mils in parallels or sticking with the 240 mil in parallels that were already installed on the job to get next to the same amount of current based on how you then designed the reference method. So those that are keen amongst you, go and have a look at the two different reference methods that you can generally apply to the regs when you've got cables and duct underground, because you've got what we spoke about today. And then there's a method called ERA, which has some other factors involved in it, which then massively can benefit your cables if you can comply with some of those factors as well. So this was stemmed from a scenario that had a huge cost saving to a client, basically.
Okay, and cost is massive, isn't it? How many jobs do you lose, Mark, through cost or yourself, Craig? Is cost a major factor?
It's always a factor, definitely, in any job you're pricing. I mean, you never really want to be bottom of that pile, but equally you want to be competitive. So it's a consideration, like Craig said earlier on, the design discussion around that for getting a safe installation, but also one that's competitive. It's not easy, and that's often the great skill that's in design.
Yeah.
I know in my world, when it goes out to tender, for every job we go for, 3 other electrical companies are asked the price.
Right.
You've all got the same information. It's what you take from that pack and what you bring back to the table that then gets you the work.
Yeah. So it's crucially important then, isn't it? Massively important. Yeah. And
it shows if you misunderstand some of those tables.
It does.
It can have a big impact if you get a figure from the wrong table somewhere or through your calculations. You can impact on your design and then maybe put yourself out of cost. So it's well worth making sure that you've got that process in place and you are happy with all your selections. Use the right column in the tables
use the right
as well.
Table. It's practice. It's checking and double checking. Just you can quite easily use the wrong table because you've not considered, just like I did earlier, that CPC was run separate and not incorporated. But that was just me transferring stuff from last week into.
Well, that came from what I'd also sent over. And when everyone's doing something in a rush, it's a clear, easy error, isn't it? And
that's good. Yeah.
What I would say to people is, we're not trying to be patronising to anybody, but when we say things about the columns and the table, it's because myself and Richard have stood in front of classes, and Mark has obviously trained a huge amount of apprentices, that people say to me, but Craig, there is 3 cores in that cable, and they don't understand that we're talking about the live conductors of the cable, not the CPC that's involved inside it.
Yeah,
it's little things like that may catch you out, that we're hoping that we can share some of what we've seen in the classroom or out in the field to help you not make those same mistakes.
Yeah, simplifying out. And I do know that in Amendment 3, at the moment, where you've got reference method D in your current carrying capacity tables, it just talks about either direct in the ground or inducting. So we've only got 2 columns for either. In Amendment 3, there are 2 additional columns coming. Just a bit of inside information for you. So there'll be 2 additional columns added. So you'll have 2 columns for direct in the ground and 2 further columns for inner duct. Because
that'll be at least another £5 on the cost of the book now if there's extra bits going in it.
But that is coming because, if you've got a correction factor to consider, either in the ground or in a duct, and depending on depth of the ground, it does have an effect on the current carrying capacity. So they do need to add those 2 additional columns in. I think it's a good idea. But another bit of useless information. But that
not
is
at all
in Amendment 3 for sure, as well as loads of other 700 pages.
This was a really, really good example again, and I know this is something that Craig's come up with and Richard's brought into the visual space and led us through the discussion again tonight. Just want to feed back to you two, really, some of the stuff that's come back on the socials through this. There's been quite a few DMs saying it's been really helpful, a much better way of understanding the found in their college environments. So there are people out there, there's probably between 20 and 30 messages along those lines, actually, from last week's episode, of people really passing on their thanks. So it is having an impact. People are getting value from it. There's been comments on the YouTube video and on the Spotify. People can comment back through there now as well. So they've answered with some improved suggestions for that scenario we popped out last week. Okay. I am going to share that again a bit more widely to give other people a chance to have a listen and get involved in that before we pick some winners, but that's been done. So there is a lot of appreciation for that. A massive thank you for putting the effort in doing it. It's brilliant. I'm a passenger on these. I enjoy it. I've sat and learned something tonight listening to you guys talk through that example. I'm not big and clever enough to sit here and say I know everything. So I very much appreciate it as well myself.
Yeah, no problem. I don't think any. I mean, every day is a learning day. I know we've had a conversation today about inverters and all sorts of stuff. You never know everything, and if I don't know, somebody will know, or somebody will have an idea of someone that will know, and that's how you build up your professional relationship with people in your working life, don't you? Because if nobody knows everything, and if you do, you're talking out your backside, I think. And as you say, there's far more clever people than me, but I just try and apply a simple approach to things, and generally, if you can simplify some of that, you kind of get there in the end. So and that's all they are, cable calcs. It's more about finding your way around the book and using the right information to get to where you need to get, really. But there you go. So I suppose it'll be my turn next week now. I think I'll I think I'll use an EV charger or something a bit relevant. Maybe
I need to ramp it up another
single phase, 3-phase, or DC. Put it in the comments.
Yeah, we'll come up with something. And we'll think about other considerations in terms of 722. We'll add a little bit of other considerations, a bit like we did last week, where we considered do I need additional protection, and we won't go too deep, but we'll have a little bit of a look, because we kind of got the flow now, haven't we, of our different steps. So we'll add a little bit of other considerations you need to consider as a designer at the end of the day. And ultimately, whatever you choose as a designer, it's going to affect your pricing and your cost, as we've said tonight. So yeah, no problem at all. I'm just glad hopefully it's useful, and that's all that matters, isn't it? It's all good.
Anything further any of you'd like to add? Sorry, Craig, carry on. I
was just going to say I'm enjoying being part of these, the way it's laid out and following through. It's good because there is bits you notice as you go through and you go, I didn't think of that, should have added that, should have thought of that. And I guess that's our real world every day, isn't it? I'm fortunate that I sit in an office full of 4 or 5 other people that are relatively okay with this stuff, and we can bounce that day to day off of each other. So even however many years we are all in asking these questions, if you're new to it, then make sure you're asking the questions and don't be shy, would be my final thoughts.
Yeah.
100%.
So. And again, even based on tonight's scenario, any additional thoughts or comments or questions, and just, post them into Mark, and I'm pretty sure we'll get together and have a chat and try and give some other advice. And these will be available again. I'll resend the one I got the wrong table in tonight. I'll resend that to Mark tomorrow, so you've got the right one. But it just goes to show we're all, at the end of the day, we're all electricians, we're all human, and you have to double check stuff, but that's life, isn't it? So.
Oh, listen, you're volunteering your time doing all this. It takes a lot of effort to get those slides into play, and I massively appreciate it. We're all sat here now at 8:30 on a night talking through it on a podcast because we like to help people and discuss things among ourselves for enjoyment. So there's no issue there whatsoever, Richard. Thanks for making the effort to even put that together. And as I said, loads of people are getting value from it. I think it's brilliant, and hopefully we can continue these for the foreseeable. There will be, again, all the files and everything in the same place as last week, but it is all in the description. If you want to go and dive back into them, jump down there and have a look. We'll be back again in a week or so with another example, and we'll see if we can move it on a bit further. The idea is we're taking apprentices on this journey with us. We don't want it to seem daunting and scary for people who are new to design and kind of building up their careers in the electrical industry. So if you're ahead of this level already, bear that in mind. We are working towards some more technically difficult things, if you want, for a better phrase, and we'll jump to that in the future. Thank you again, both gents, for joining in, and we'll see you on the next one.
No problem. Cheers, everyone. Cheers.
Bye-bye.